Good morning, one and all. Myself Sreevani, working as an assistant professor in the Department of Electronics and Communication Engineering in Inst of Aeronautical Engineering, Dundigal, Hyderabad. So, in the today's lecture, we are going to learn about introduction to transmission lines, then types of transmission lines, and different parameters of a transmission lines. Right? So, before going to in detail discussion about this transmission lines and all types of transmission lines and the parameters involved in the transmission lines, first let me introduce about the definition of a transmission line, and after that we are going for different types of transmission lines. Then, depending upon the frequency ranges, different types of transmission lines can be used, and what are the different ranges of frequencies of that respective transmission lines, then followed by what are the different parameters of transmission lines we are going to discuss in this particular lecture. Now, a definition of a transmission lines, right? So first, a transmission line is a structure intended to transport electromagnetic signals or power. Means a transmission line is a structure intended to transport electromagnetic signals or power. Transport means we have to send some information or energy or signals from one place to the another place. That first place is said to be source and the next place is said to be destination, or source and loads, right? Source is always considered at the input side and loads may be always connected at the output side, right? So the fundamental definition of a transmission line means it is a structure intended to transport electromagnetic signals or power from one place to the another place. Or in another ways, we can define these transmission lines as transmission lines or guided conducting structures. Guided conducting structures which are used in power distribution at low frequencies, in communications and computer networks at high frequencies, right? So transmission lines or guided conducting structures which are used in power distribution at low frequencies in communications and computer networks at high frequencies. So depending upon the frequency ranges, we will use different types of applications in transmission lines. Then in another way, transmission lines are used to transmit the electrical signals and energy from one point to the another point, right? So in general, we can define this one as transmission lines are the lines which are used to transmit electrical signals or energy from one point to the another point, right? So that first point is said to be source and the next one is said to be load. Then the basic transmission line connects a source to a load. Usually it consists of two conductors. Means basically transmission line consisting of, means previously how we have defined transmission lines or guided conducting structures, means basically it consisting of two conductors, right? Depending upon that, inside that conducting structure, it is able to transmit electrical signals or power from one place to the another place. Means there must be from source to the destination, or to send energy or power or signal, we need a physical connection. That's why it is a guided conducting structure which can able to transmit electrical signals from one place to the another place or one point to the another point. Means the basic transmission line connects a source to a load and usually it consisting of two conductors, right? Depending upon this structure, means it connects source to a load. Means what is what are the different examples for sources and what are the different examples for loads. Now we are going to see here. See, sources may be some of the examples for sources. Some of the examples for sources may be hydroelectric generator. So the fundamental one is an example for sources, is an example for your generator. Hydroelectric generator, which is able to provide input source to the input to that particular device. And a transmitter, always we used to connect this one at the input side, transmitter, in order to transmit signals or energy or power. We must connect this particular device at the starting point or input side. And an oscillator. So it is also a device which is able to generate different types of signals. So here some of the examples for sources may be given by hydroelectric generator, a transmitter and an oscillator. So it is a device which is able to provide always sinusoidal oscillations, nothing but oscillator. And some of the examples which are connected at the outputs means those are considered to be as loads. And loads may be given by here a factory which is able to deliver or which is able to produce, hence the outputs are to be considered at a factory. And an antenna which is transmit and it can acts like a transceiver, and a device it is acts like a transceiver is an antenna, and an oscilloscope. So in order to generate different types of signals, in order to display that all such signals, we use one of the device called oscilloscope, nothing but CRO. Okay. So these are all the different examples for sources which are connected at the starting point, that is nothing but input side, and loads may be which are connected at the output side or receiver side. All are connected at the transmitter side, and these are all connected at the receiver side. All are examples for sources and these are all examples for loads. Okay, so basically transmission line is a guided conducting structure which can able to transmit electrical energy from source to a load. So here are some of the examples for sources and loads. Then based upon that we can define in general, in short, a transmission line is a two conductor system which can guide electromagnetic energy, right? So before going to in detail discussion about this transmission lines, in the first three modules we have discussed in the electromagnetic waves and transmission lines. First, in the first module we have discussed about all static electric fields, also called as electrostatic fields. In the module 2 we have discussed magnetostatics and followed by time varying fields. Then those time varying fields are also called as Maxwell's equations. And in the third module we have discussed all the wave propagation characteristics of free space medium, and depending upon the conductivity of the materials, different types of medium we have discussed: dielectric medium propagation characteristics and conducting medium propagation characteristics. Now so there is a fundamental difference between transmission and propagation. What actually these two are used to send, or these two are used to transmit information from one place to the another place. So transmission requires a physical connection from the source to the load, whereas propagation doesn't require any physical connection. Means in order to send the information in without applying any physical connection, without considering any physical connection, the process is said to be here propagation. With the help of physical connection, it is said to be transmission. Right? So here now we are discussing about transmission lines. So there are different types of definitions we have seen. Then in general, in simple way, we can define the transmission line as a two conductor system which can guide electromagnetic energy. Right? Electromagnetic energy. Now, another ways. A transmission line is a connector which transmits energy from one point to the another point. Right? So in short, we'll represent or we'll define it as a transmission line is a connector which transmits energy from one point to the another point. And the first point is generally source and the second point is generally known as load, or it may be a transmitter and receiver also. Right? Source is nothing but transmitter and the load is nothing but here receiver. Okay. So transmission line is a connector which transmits energy from transmitter to the receiver, or which transmits energy from source to the load. While transmitting and receiving, while sending the information from one point to the another point, the energy transfer has to be done effectively without the wastage of the power. Right? This is the main criteria which we are going to consider in this particular transmission lines. Means in order to send or in order to receive the data, while transmitting and receiving, the energy transfer has to be done effectively without the wastage of the power in the transmission lines. Then the study of transmission line theory is helpful in the effective uses of power and in the equipments. Then coming to the, so first we have learnt about what do you mean by transmission lines and how many different ways we can define transmission lines we have seen just now. Now coming to the types of transmission lines, different types of transmission lines, right? So depending upon the frequency ranges, there are different cases of transmission lines are available. So there are basically 4 types of transmission lines based on structure and frequency. Okay, so depending upon the frequency and depending upon the structure of a transmission line, there are basically 4 types of transmission lines are there. First one is 2-wire parallel transmission line or open wire transmission lines, right? 2-wire line or open wire parallel transmission lines. In this we can transmit the signals, the range will be up to 100 megahertz, right? So if you want to send the signals more than 100 megahertz, it is impossible through parallel wire transmission lines. That's why we are going for next type of transmission lines called coaxial cables. So in this coaxial cables, the frequency range will be up to, we can transmit the signals from 100 megahertz to 1 gigahertz. If you want to send a signal more than 1 gigahertz, it is not possible in coaxial cables. Then we are going for next guided conducting structures called waveguides. In this we can transmit signals up to 3 gigahertz. Means in order to send ultra high frequency range more than that of 3 gigahertz, we use the last case called fiber optic cables. In this, more than 3 gigahertz signals frequencies we can transmit through this fiber optic cables. Okay, depending upon the structures and depending upon the frequency ranges, there are 4 types of transmission lines or exist. First case as 2-wire parallel transmission line. These two are also called as 2-wire, means basically it consisting of 2 parallel conducting lines. So open wire transmission lines, these are the 2 conductor 1 and conductor 2. So inside, in order to transmit the signals from one place to this one, there exists physical connection from this place to this place or transmitter to receiver. So examples for this is telephone lines and power lines, right? High tension wires are a best example for this power lines. So next, now to send more than that of 100 megahertz signals, then we use coaxial cables. Those are second type of transmission lines. Examples for this coaxial cables are long distance telephone transmission lines and television transmission lines, and one of the best example we are seeing daily as LAN connection, local area network connection. So inside it uses coaxial cables. Through this coaxial cables we can transmit up to 1 gigahertz signals frequencies. Okay, then in order to send more than that of this 1 gigahertz, third type of transmission lines are called waveguides. In this we can transmit up to 3 gigahertz as the signal frequencies. Examples are broadband communications or best example for this waveguides. Different types of waveguides are there, rectangular type, tear type, different types of waveguide structures are available. So fourth type of means in order to send the signals more than that of 3 gigahertz, we use coaxial. Another type of transmission lines called fiber optic cables. Then cable television is an example for best example for fiber optic cable. In this we can transmit signals range up to more than 3 gigahertz. Okay, in detail, the physical structure of symbolic structure of diagrammatic representation of individual transmission lines we are going to see now. So first case, two wire parallel transmission lines or open wire line transmission lines. So basically it consists of the physical connection, means these are the two conductors 1 and 2, then it carries, means if the conductor 1 the current direction will be like this, and in the conductor 2 current direction will be opposite to that of first, and the distance between the length of this is given by here d, and these two are separated by a small dielectric material as epsilon. Okay, so it consists of two parallel conducting rods. These are the two parallel conducting rods, and in this case the electrical energy is distributed in open wire or two wire parallel transmission lines case. Basically it consists of two conducting rods. In this case the electrical energy is distributed between and around the rods, right? So physical connection between means how we can identify these are the means the high tension wires or best example for the two wire parallel transmission lines. Then and the equivalent circuit of this will be, means the physical two wire transmission lines are looks like this. Then from this equivalent circuit with the partial inductances and resistances as represented like this. Inductance is LP and the resistances are like, and the simple equivalent circuit with loop inductance and the resistance, means this is the fundamental transmission line equivalent circuit. So what are the components it consisting of, means one is this capacitance, inductance, resistance and conductance. Means basically there are four fundamental constants or primary parameters of transmission lines or exist, that is resistance or inductance L, conductance G and the capacitance as C, right? So resistance R is measured in ohms and the inductance can be measured in henries and the conductance can be measured in mhos and the capacitance can be measured in the farads, right? Throughout the length of the transmission line, these are all uniformly distributed. Hence, throughout the length can be measured per kilometer, per kilometer, per kilometer, and per kilometer. Right? Length of the transmission line, generally it is measured in kilometers. Hence, those two, resistance of this transmission line, inductance, conductance, and the capacitances, these four are called primary constants of a transmission lines. Okay, so in general the two wire parallel transmission lines or looks like the physical two wire transmission lines which are consisting of two conducting rods, and inside that the electrical energy is distributed between around the rods, and in this we can transmit the signals range up to 100 megahertz. If you want to send more than that of this 100 megahertz signals range, then through this it is not possible. Then we are going for second type, that is coaxial cable type transmission lines, right? So it looks like, means basically it consisting of two conductors separated by a dielectric. Dielectric is nothing but insulating material which has conductivity sigma equal to 0. So two conductors separated by dielectric, both the conductors are having common axis, hence the name coaxial has come. Okay, there is a connection between this outer core and inner core, hence that's why the name has given as coaxial cable, right? So here also outer core means let it be outer conductor and inner core means it is another conductor, Basically, transmission line consisting of two-way conducting structure means it consisting of two conductors. So first outer conductor has one and inner conductor has one. Inside there is a dielectric material which is separated by those two, and the spacing between two will be very less. Okay. See, planium outer jacket and inner jacket and bladed sheet. This will be identified with the dielectric material, right? So in this we can transmit up to the signals as 1 gigahertz. Means 100 megahertz. If you want to send the signals, range will be 100 megahertz to 1 gigahertz. It is possible through coaxial cables. Suppose if you want to send more than that of this 1 gigahertz, then it is not possible through this coaxial cable. Then we are going for third type of coaxial transmission lines called waveguides. Okay, so circular waveguide, rectangular waveguide, different types of waveguides are there. Here is an example for rectangular waveguide. Basically, it also consisting of two conducting rods, right? So waveguide is a special form of transmission line which is a hollow metal tube. So this is one of the type of waveguide. And unlike a transmission line, a waveguide has no center conductor. So separately we can have. Then the tube wall provides distributed inductance, and the empty space between the tube walls provided distributed capacitance. Basically, the transmission line consisting of what are the four primary constants? RL, GC, resistance, inductance, capacitance, and conductances, right? So here waveguides are a special form of transmission lines, which is an example here we are going to see here is the metal tube type, hollow metal tube type, and here is an example for rectangular waveguide type. So through this waveguides we can transmit up to signals 3 gigahertz. Through this we can transmit up to 3 gigahertz signals. Suppose if you want to transmit more than that of 3 gigahertz, then it is not possible through waveguides. That's why we are going for next type of transmission lines called fiber optic cables. Okay, so optical fiber cables are transparent and flexible. The highest signal frequencies are to be transmitted through this fiber optic cables. So nowadays the usage of this one is very in number of applications are used this fiber optic type of cables. So optical fiber cables are transparent and flexible. The usage is also very easy. Then fibers made up of glass or plastic through which light waves can pass. And in this we can transmit signals more than 3 gigahertz. Right? Ultra high frequency ranges signals are to be transmitted through this fiber optic cables. Right? So it consists of two dielectrics, core and cladding with different refractive indexes. So as we know that for a refractive indices means diffractive index is denoted with N and it is given by C by V, where C is the velocity of light in free space and VB the velocity of light in medium. Depending upon the medium we will consider over there, right? So it is also a type of transmission line, means basically consisting of two conductors and which are core and cladding. Internally we have copper wire. Through that the energy or the electrical energy or signals are to be transmitted over a long distances. Means in this we can transmit up to 3 gigahertz of the signal frequencies. Right? So these are all the different types of transmission lines. First case we have considered is open wire type transmission lines, and the second one is coaxial type, and the third is waveguide type, and the fourth one is fiber optic type. Fiber optic cables. So in the open wire type we can transmit signals up to 100 megahertz, and in the coaxial cable this more than 100 megahertz to less than that of 1 gigahertz, and in the waveguides this less than that of 1 gigahertz to means more than up to 3 gigahertz, the signals are to be transmitted through waveguides, and more than 3 gigahertz signals are to be transmitted through this fiber optic cables. So the advanced type of transmission lines means comes under fiber optic cables types only. Means the long distance travel purpose, signals transmission purpose, we use one of the type of transmission line called fiber optic cable. Next, different types of transmission line parameters. Basically what it consisting of means the important parameters of a transmission line are resistance is denoted with R, inductance is denoted with L, capacitance as C, and the conductance as G. Right? These parameters are known as primary constants of a transmission line. So there are two types of constant consisting of this transmission lines. One is primary constants and the second one is secondary constants. Right? So what are the different primary constants of a transmission line means resistance or inductance L, conductance G, and the capacitance C are called primary constants or primary parameters of a transmission line. Right? So secondary constants means characteristic impedance as Z0 and propagation constant gamma are called as two secondary constants of a transmission line. So generally this resistance or inductance L, conductance G, and the capacitance C are distributed throughout a length of the transmission line. Means basically the length of throughout means if you consider along a transmission line, one of the parallel wire type or open wire type, see suppose if the length will be up to 1 kilometer. So throughout each subsection means each section that length of 1 kilometer is divided into subsections with a lumped elements. Means in the lumped network it consisting of only 4 primary constants. Suppose if you combine all lumped elements throughout that 1 kilometer length, then such type of networks are called distributed networks. Means all the lumped elements are distributed throughout that length of the transmission lines. Okay. So here is the simple circuit diagram for the equivalent circuit of a transmission line, and basically consisting of lumped networks. Each lumped network consisting of 4 primary parameters as resistance or series inductance as L, shunt conductance as G, and the capacitance as C. Means resistance R and the inductance L are connected in series, whereas conductance G and the capacitance C are connected in shunt. Right? Suppose if you observe the connection between these two are in series, and conductance G and the capacitance C, if you observe, these two are connected in parallel. How we can identify if two elements are connected in series and if the two elements are connected in parallel? Means if the connection between two elements are to be identified as series, depending upon that, means if only one end is common between those two elements, then those two are said to be in series. If the node to node connection is exist, means starting edge and ending edges are same for the two elements, then those two are connected in parallel, or this parallel connection sometimes is also called as shunt connection. Shunt connection is nothing but parallel connection. So out of all these primary constants, two are connected in series and the rest of the two will be connected in parallel to that rest. Means resistance R and the inductance L are to be connected in series, capacitance C and the conductance G are connected in shunt or parallel connection. So here is the simple circuit diagram for the transmission line, and in each transmission line, in each lumped section, it consisting of 4 primary constants as R, L, C, G. Resistance, inductance, capacitance and conductance. Okay. So there are two types of primary constants or parameters of a transmission lines are there. Primary constants and the secondary constants. Then resistance or inductance L, capacitance C and the conductance G are said to be primary constants or primary parameters of a transmission line, and characteristic impedance Z0 and the propagation constant gamma are represents secondary constants of a transmission line. Next, to understand or design a transmission line, it is necessary to know the electrical parameters that are associated with the transmission lines, right? So in order to design a particular transmission line, we need to know what are the electrical parameters which are associated with that particular transmission line. And if a parallel wire carrying a current I, then magnetic field will be generated around that wire and voltage is developed along the line, right? So if a parallel wire which is carrying a current wire I, then the magnetic field will be generated around that wire, means around that coil, the current which is flowing through this coil, and there we are going to develop, it is going to develop voltage which is to be provided for that in order to operate that coil, in order to generate that coil as magnetic field. Then due to magnetic field and the current, there will be series inductance. Due to voltage along the line, there will be a series resistance. Okay, so when we apply, means series resistance and series inductance, means the equivalent impedance can be written as Z is equal to R plus J omega L. R is nothing but resistance of that transmission line, L be the inductance of that, J omega, omega be the angular frequency of the line, and J represents here. Basically, there are two reactive elements. One is inductance as L, XL, and the another one is capacitance as XC, reactive capacitance, that is represented with XC. XL is represented with J omega L and XC is 1 by J omega C. Capacitive reactance and inductive reactance. Okay, so depending upon that, here resistance R and the inductance L can be connected in series. Then the equivalent impedance can be written as Z is equal to R plus J omega L. Next, when we apply voltage between two conductors, electric field will be generated. Due to this, there will be shunt capacitance C and the shunt conductance G. Now from these two, we can write it as G plus J omega C. Right? That is Y equal to, admittance Y is equal to G plus J omega C. Why we have considered here as the impedance and here as the admittance means the conductance and the capacitance both can be connected in the circuit as in the shunt manner. Shunt means the reactive elements can be represented as 1 by G and 1 by XC. Then we are going to consider, means there is a relation between admittance Y and the impedance Z, or Z is equal to 1 by Y or Y equal to 1 by Z. Two are reciprocal to each. Hence, we are writing the impedance Z is equal to 1 by admittance, or admittance Y equal to 1 by impedance. Based upon this, the series inductance and series impedance and shunt admittance can be considered as Z is equal to R plus J omega L and Y equal to G plus J omega C. Next is the primary elements are distributed along the transmission line uniformly. So what are the primary elements here? Resistance R, inductance L, conductance G and the capacitance C. So RLGC parameters are distributed along the line, along the transmission line uniformly. Hence the name, means the transmission lines is called as uniform transmission line. Means throughout the transmission line RLGCs are uniformly distributed. Hence the simple transmission line is also called as uniform transmission line. Next, where R is the loop resistance per unit length, then sum of the resistances of both the conductors per unit length. Hence the unit for this is given by ohms per kilometer. In general, the resistance is measured in ohms, and throughout the transmission line, means the length will be given by here per kilometer. Hence resistance R is measured in transmission lines as ohm per kilometers. And L is the loop inductance per unit length, that is sum of inductances of both the wires per unit length, and the unit for this inductance can be measured as Henry per kilometer. Generally, inductance can be measured in henries. Then for a transmission line means per kilometer, that is given as R, and here it will be the L. Okay. Similarly for conductance and the capacitance. As C is the capacitance between the conductors per unit length, and its unit are given by here farad per kilometer. Generally, the capacitance is measured in farads throughout the length of the transmission line, means that length will be considered as per unit per kilometer. Hence, in transmission lines, the capacitance, one of the primary parameters C, is measured with respect to the farad per kilometer. And the conductance G is also connected in the shunt manner, like here this is measured mhos per kilometers. Why? Because this conductance G and the resistance R both are reciprocal. Hence, the resistance is measured in ohms and the conductance G is measured in mhos. In general, it is measured in mhos. So throughout that length of the transmission line, means unit for that conductance, shunt conductance, is given by mhos per kilometers. Right? So as series impedance Z is given by R plus j omega L, and shunt admittance Y is given by G plus j omega C. Based upon that simple equivalent circuit, lumped equivalent circuit, RL GC. So okay, this is the simple equivalent circuit output, and here is the input. Okay, the parameters or the primary constants which are associated in this particular transmission line are given by R, L, G, C. Right? So if you observe from this, the equivalent impedance Z can be written as Z, and here it will be the Y. So Z is equal to R plus j omega L, and Y equal to G plus j omega C. Okay, so from the lumped equivalent circuit, from the primary constants equivalent circuit of a transmission line, then series impedance Z can be written as R plus j omega L, and shunt admittance can be written as G plus j omega C. Next, so now depending upon the components which are exist in the transmission lines, there are two types of parameters in transmission lines. One is lumped parameters and another one is distributed parameters. Right? There are two types of parameters in a transmission lines: lumped parameters and distributed parameters. Suppose if you consider the first case as lumped parameter section, what it consisting of? Transmission line, what it consists of, then how it is to be formed. Means at high frequencies, as the wavelength, means wavelength is generally represented with lambda, then that is given by 2 pi by beta. Wavelength. So 2 pi radians, within a 2 pi radians the phase is going to change. According to that, the wavelength can be defined as lambda equal to 2 pi by beta, where beta is the phase constant and 2 pi be the phase. At high frequencies, as the wavelength will be small and comparable to length of the transmission lines. Means as the high frequencies, as the wavelength will be small. At high frequencies, the length of the wavelength will be small and it is comparable to the length of the transmission line. How it is comparable means depending upon the lumped and distributed sections. If we divide the total transmission line into small sections, the length of the transmission line is to be considered, for example, 1 kilometer. So for each 100 meters, we will divide the total into subsections. Each subsection means for 100 meters, we'll have one lumped section. Next 100 meter, we'll have another one lumped section. Like that, the length of that will be divided into small sections, such that length of the small section can be neglected as compared to the wavelength. Right? So these small sections, each small section is called as lumped elements. And what it consisting of means the primary constants of a transmission line. So what are the primary constants of a transmission line? Resistance or inductance L, conductance G, and the capacitance C. Okay. So lumped elements means it consisting of all the primary constants of a transmission line. The lumped element analysis is to be applicable at all frequencies. Okay, this small section equivalent circuit is applicable for all the frequencies ranges. Then next is distributed one, distributed type of parameters. The parameters RLGC or or called as primary constants of a transmission line. Line in the sense transmission line. They represent various electrical quantities of the line that are distributed throughout the length of the transmission line. Means this is one lumped section, this is another lumped section, and this is another. If it is goes on continues till the end of that physical connection which is exist between source to the destination, each lumped section, each part of all the primary sections are called lumped sections, and that each lumped parameters networks are distributed throughout the length, then the parameters are said to be distributed parameters. Okay, so what we have discussed in this particular lecture is different definitions of a transmission line. Then what is the fundamental difference between transmission and the propagation, and after that we have discussed different types of transmission lines as depending upon the structure and depending upon the frequency components. There are 4 classifications under this transmission lines. Those are open wire type, coaxial cable, waveguides type, and highest applications used transmission line as optical fiber cable. Depending upon that frequency ranges, those 4 types of transmission lines we have discussed. Then after that, primary components or primary elements of a primary constants of a transmission lines we have seen. Those are said to be resistance or inductance L, conductance G, and the capacitance C. Then followed by we have discussed a simple concept called lumped section elements and distributed section elements. Each primary components section is called lumped section. Then in the distributed section, all the lumped parameters are distributed throughout the length of the transmission lines. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.